Okay. So, what do you mean by slab? I hope all of you have seen some concrete slabs, right? So basically, similar to beam, what will happen to slab is that when it is subjected to some sort of loading, it will undergo bending. Okay. So we have two types of bending that can occur in the case of a slab. Say, when you consider a slab like this. Okay. So you have a room which is having one dimension very large in compared to the other dimension. So when this is subjected to load, what you can expect is that this will be actually, say you will be having support here on this side throughout this portion. Similarly here also you will be having support. Okay. So in this type of slabs, what will happen is that the bending normally occurs in this way. So if you are looking from this side, this slab will be actually bending like this. Say, for example, you can consider your long notebook. Say you will be having a notebook having some dimension like this, and if you are holding it in your hand, you may see that the bending will be predominant in this type of, in this direction. Okay, and there can be another case, say where you have something like this. Okay, so almost a square paper. Let's take a square paper and let's hold it in our hand and apply some load on top of it. How will be the bending? Or better than the paper, you just assume you have a textile piece. You have a piece of cloth which is having dimension like this, and you are just holding it on four sides. So what will happen to the cloth actually? If you are looking from this top side, it will have bend like this, and if you are looking from this side also, you can see that there is a curvature like this, because in this case actually the bending is actually happening in both the directions. So based on this, that is based on how this slab bends when it is subjected to load, we have classified slabs into two cases. That is, one is one-way slab and another one is two-way slab. As the name suggests, one-way slab means the bending will be predominant along one direction alone. As this case, the bending will be predominant along one direction. Whereas in the case of two-way slab, the bending will be predominant in both the direction. Okay, so that is how this classification is made. So basically, when we subject load on a slab, and based on how this slab bends, we are classifying the slabs into two groups. One is one-way slab and another one is two-way slab. One-way slab means the bending will be along one direction, whereas two-way slab means the bending will be along two directions. Okay, so now the problem is how to know. Say we have to anyway design it. So how to know that I have a slab with me, and whether when I subject some load on it, how this slab will bend. How to know that before actually constructing the slab? That was a problem. So what people have done is that people have conducted lot of experimentation, and they have observed that when this ratio, that is Ly by Lx ratio, is larger than 2, we can consider that to be a one-way slab. So in majority of the experimental results, they have observed that when the Ly by Lx ratio is greater than 2, and please note, Ly will be always the larger dimension of your slab. Say suppose you have a slab like this, okay, then your Ly will be this value, and your Lx will be this one. And suppose you have a slab like this, where you have a larger dimension along your x-axis, your Ly will be here, and Lx will be this length. Okay, so based on these different experimentation conducted on slabs, people have observed that if the ratio of Ly by Lx is greater than 2, the bending will be normally predominant only along a single direction, and they call that as one-way slab. Whereas if Ly by Lx is less than 2, the bending will be predominant in both the direction, and so they call them as two-way slabs. So please, what you have to understand is that this is just for classification, for working out the design purpose. We need to have some methods by which we can classify slabs into one-way and two-way. So for that, we have just developed this type of equation based on experimentation. Okay, but the concept is that when we subject load on a slab, and if the slab is, the bending of the slab is actually predominant along a single direction, they should be called as one-way slab. And if the bending is predominant along both the direction, we have to call them as two-way slab. And why we need such a classification? That is the next problem. Okay, say suppose I have a slab, say I will just draw like this. I have a slab like this. I have a slab like this. Okay, so this is my Ly and this will be my Lx. So from this figure itself, let's assume that Ly by Lx is actually greater than 2. Okay, so it will be a one-way slab. If Ly by Lx is greater than 2, it will be a one-way slab, and the bending in this case will be predominant along this direction. So the slab will have a bending like this. Okay. Now my question is how to design it. So basically, in the case of beams, we have seen that when we have a beam like this, it will actually bend in this manner, and we have provided reinforcement in the tension zone. And since this bending is happening in this direction, in order to prevent this bending, what we have done is we have provided our reinforcement like this in the tension zone. Okay. And now I again have a slab here, which is actually bending like this. So basically, if you are checking out the three-dimensional shape, it will be something like this. So basically, what we have to notice that since this slab is actually bending along or about an axis like this, if you see from this side, it is actually bending about this axis. So what we have to do is that you have to provide reinforcement in this direction in order to prevent the bending of this slab. Since this slab is actually bending like this, you have to provide reinforcement here to prevent this bending. So you just visualize, practically think, when we have something bending in one direction, we have to actually provide reinforcement in this direction to prevent that. Say, let's take the other example. Say, if I have the same slab and this was actually bending like this. Okay. And I am just, in order to prevent this bending, I am just providing reinforcement in this direction. Will it be effective? What is your opinion? Will case A be effective or B? Which one will be effective?
A.
Any other answer other than A? See, this will not be effective. Once this thing is actually undergoing bending, what will happen? These reinforcement will remain here. That will not have any role in resisting this reinforcement. So what we have to understand is that in the case of one-way slab, since the bending is predominant in one direction, we have to actually provide the main reinforcement in order to prevent that, and that too in this direction along Lx direction. Okay. So what about two-way slab then? Say we have a two-way slab like this. This is actually having bending like this if you are looking from here, and if you are looking from this side also, we have some bending like this. So what we will do? In which direction we will provide reinforcement in case C?
Both the directions?
Exactly correct. So since we have bending in both directions, what we have to do is that we have to provide, first of all, in this direction, then we have to provide reinforcement in this direction. So these reinforcement will take care of this bending, and these reinforcement will take care of this bending. So this is what we usually do in the case of two-way slab. In the case of two-way slab, we will provide our main reinforcement or reinforcement to prevent the flexure in both the direction, whereas in the case of one-way slab, we will be providing it only along the direction which is having the predominant bending. Is the concepts clear to you? How we classify the slabs and what is the significance of this Ly by Lx ratio and all? Any doubts in this for anyone? It's clear. Okay, so let's proceed further. So when you design a slab, your first step is to ensure or understand whether the bending will be along one direction or two direction. That is, by that I mean, you have to actually classify the slab into one-way slab or two-way slab. Then you have to design it accordingly. And one more thing is that in the case of one-way slab, say something like this, what will happen is that normally the load, say when we apply, we will be applying a uniform load on throughout this slab, right? So what will basically happen is that the load will be actually, the load will be actually transferred like this in this pattern. Sorry, not in the case of one-way slab. In the case of two-way slab, please note, this is in the case of two-way slab. The load will be actually transferred like this. That is, this much load, say this load represented by this trapezoidal portion, will be transferred to the support on this side. And this portion will be transferred to the support on other side. The load acting on this area will be carried by the support at this location, and finally this triangular load will be transferred to the beam or the support provided on your right side, and this one will be taken care of by the support provided on your left side. So this is the load transfer pattern normally observed in the case of two-way slab. In the case of one-way slab, what will happen is that this will be the pattern. Say you can directly split it into two halves, and half of this will be taken care of by the support in the top portion, and the remaining half will be taken care by the support in the bottom portion. So this is how the load transfer take place in the case of a one-way slab. So please don't confuse with the name given here. See, for one-way slab, the load pattern is like this, and the ratio will be Ly by Lx is greater than 2. And for two-way slab, the load distribution will be like this, and the Ly by Lx ratio will be less than 2. Once you are clear about the design of beams, this is typically the same thing, only with minor modifications. Say we will actually design the slab as a beam, but only difference is that this beam will be always having a width of 1000 millimeters. That is 1 meter. So basically we will be having a beam like this, but in this case the depth is actually less compared to the width of the beam. The width will be normally considered as 1000, and this will be having a thickness. Okay. So this is the concept of design. So one-way slab is designed as a beam having width 1000 millimeters. For easiness, you can just assume like that. One-way slab is designed as a beam having width of 1000 meters. And in this module, we will be dealing with the design of one-way slab alone. And the next module, we will be dealing with the design of two-way slabs. So that is regarding that. Now, the relation for neutral axis, moment of resistance, calculation of area of steel, effective span, control of deflection, etc. used for beams are also applicable to one-way slab. So if you refer IS 456, there you can see that these conditions are actually applicable to your slabs also. The conditions which we used for design of beams are actually applicable to slabs, but there can be slight variations. So you have to actually go through that and just ensure that you are taking into account those modifications. Okay, so and while doing the problem, we will just explain that what are the things that should be taken care of. You can please note this problem now, and after that I will explain how to do this, and after that you can do it. Okay, so let's see. So what will be our first step? Can anyone tell me what will be our first step in the design?
One-way slab and a two-way slab. I'll check.
Yeah, very good. So basically, as I have already mentioned, first thing is that we have to classify it as one-way slab. We have to check whether it is acting in one direction or two direction. So for that, what we require is we need to calculate the Ly by Lx ratio. And before that, they have just mentioned the data given in the question. That is, width of the support is given as 250 millimeters. Then the clear span. So because we have a room like this, and the inside dimension is actually given to you. Okay, the inside dimension is given to you, but you already know that you will be having some sort of supports around this room. Sometimes it will be wall, sometimes it will be beam, or likewise sometimes it will be directly resting on some columns or some other support. Okay, so basically right now we have only this inside dimension, which will be the clear span of the slab. Okay. And in order to calculate the effective span, you can again use the clauses corresponding to your beams. So we will see that. Now, it is mentioned that we have to use M20 grade concrete and Fe 415 grade steel. Now, let's assume that a live load of 2 kilonewton per meter square is acting on this, and a floor finish of 1 kilonewton per meter square is again acting on this. What do you mean by floor finish? So if you are considering the cross section or the sideways cross section of a slab, so you will have the wall here, and you will have the slab upon this. After that, on top of this, what you will do is that you will provide some tiles or marble or granite or something like that, right? So these things will be again having some weight. So that will be again acting on the slab as a self weight. So that is what we consider as your floor finish. Sometimes you will be providing some mortar on this, and after that you will be providing some some paste to glue the tiles, and after that you will be placing the tiles. So those constitute your floor finish, and normally we will take it as 1 kilonewton per meter square, and we will assume a live load of 2 kilonewton per meter square. Again, this depends on the type of building and the area which you are designing. So what you can do is that if you want to ensure that you are taking up the right load, you can refer your 875 code corresponding to your code that gives the details of the loads. Okay. So right now in this problem, they have taken live load as 2 kilonewton per meter square and a floor finish of 1 kilonewton per meter square. Now, what we will do is that they are just calculating the effective span. Okay, so as per clause number 23.2.1 of IS 456, span by depth ratio. What was this? This was regarding your control of deflection. That is again applicable in the case of your slabs also. So let's take the code and look whether we have some difference there. The vertical deflections limits may generally be assumed to be satisfied provided that the span to depth ratios are not generally greater. The basic value of span to effective depth ratio for span up to 10 meters. So basically they are these things are actually applicable to your beams also. Nothing is specially mentioned like it is just applicable for beams alone. Okay, so the basic value of span to effective depth ratio they have mentioned was, for cantilever it was 7 meter, for simply supported it was 20, and for continuous beam it was 26, and some other conditions are actually given below that. Anyway, we have to utilize these conditions, so we will come back here later. So for the time being, what I am doing here is, I am just taking the required span to depth ratio, that is 20, corresponding to a simply supported beam, and from this I am just getting the value of effective depth, and in this case I have obtained it as 200 millimeters. So please focus here. We have some slight confusion. There can be some confusions here. So what we do here is that based on control of deflection, we are getting a value of 200 millimeters. That is 20 centimeters. That is the required depth that should be provided to prevent the deflection. But in the case of slabs, please do understand. And can someone suggest what is the normally adopted thickness for a slab in the case of a residence building? Or maybe in the case of commercial building? So basically we will be providing a thickness from 10 to 15 centimeters. That is 100 to 150 millimeters. That is the normally adopted thickness. In certain cases we will be providing 20 centimeter and all, but in the normal case, in the normal situation, we will be sticking on to a measurement between 10 centimeter and 15 centimeter. Okay, so we don't usually provide a higher value than that. That will be more than sufficient in the case of slabs. So what here I am doing is that even though I have obtained a value of 200 as the minimum requirement, I am just assuming my effective depth to be 12 centimeter or 120 millimeter. But I am just not making this mere assumption. In a later stage, I will prove that this depth is sufficient to satisfy the control of deflection. Please note, in a later stage, I will prove that this depth is enough to satisfy the control of deflection. At the corresponding location, we will see how to do it. Okay, for the time being, you just understand, even though we are getting a higher value, we will be selecting a value something like 12 centimeter or 14 centimeter, like that. Okay, so here I have taken it as 12 centimeter. Then I am assuming a clear cover of 15 millimeters, and the diameter of main bar as 10 mm. Okay, in the case of slabs, please don't provide bars like 16 mm, 20 mm or 25 mm. Okay, you have to provide something like 12 mm bars or 10 mm bars. So here I have provided it as 10 millimeter bars. So the overall dimension will be my effective depth plus clear cover plus half of diameter of my bar. That constitute or comes around 140 millimeters. Now let's see what they have done. They are now just calculating the load that will be acting on this structure. So calculation of design, bending moments and shear force. So for the slab, right now I know the overall dimension. Overall dimension is 140 millimeters. And again, you can please note that this is again less than the initial value that we obtained. Okay. Now based on that, what I am doing is that my width of the slab is 1 meter. Okay, so basically please keep that in mind. When you design a slab, you will take the width as 1 meter and you will be finding the reinforcement required in that 1 meter, and you will be repeatedly providing the same reinforcement for the full length of the slab. So we will be more clear once we complete this problem. So for the time being, for calculation of self weight of slab, I have the overall depth, then the width as 1 meter, and finally unit weight of concrete. Therefore I will obtain it as 3.5 kilonewton per meter square. This is meter square. Okay. Now the finishes, we have already assumed it as 1 kilonewton per meter square. So therefore the total dead load will be equal to 3.5. Please note the total dead load will be equal to 3.5 plus this floor finish, that is coming around 4.5 kilonewton per meter square. Now we have already assumed that we will be having a live load of 2 kilonewton per meter square. Therefore the total factored load will be equal to 1.5 times this 2 plus 4.5. 4.5 plus 2, which will constitute, or which will come around 9.75 kilonewton per meter square. So this is the total load that we can expect in our slab, and that is again the factored load. Now let's calculate the effective span for this. Again, using the same clause, we can see that the effective span for simply support beam was actually what was that? It was the clear span plus effective depth, or the center to center distance between the support. Okay, in this case, the effective depth was 120 millimeters and the width of the support was 250 millimeters. So first of all, let's take the center to center distance. That will be equal to 3.5 plus, say we will be having the slab like this, and we will be having two supports on each ends, and this is having a width of 250 millimeters, and again here we have a width of 250 millimeters. So this distance will be this clear span plus 250 by 2 here, and also 250 by 2 here. So adding this up, we will have a single 250. That is why we have written it as 3.5 plus 0.25, and this constitute, or this comes around 3.75 meter, or clear span plus effective depth, and in this case it is observed as 3.62. So basically we have to select the smaller of these two values. Okay, that is as per our IS for physics, and we observe that 3.62 is the smaller value. So the effective span will be taken as 3.62. Now with using this effective span, what we will do is that we have to find out the bending moment. So here the bending moment will be equal to WL square by 8. You already know that. So substitute the corresponding values. This is your effective span. This is the factored load that is actually acting on the structure, and you will be getting the factored bending moment as 15.97 kilonewton meters. We will also calculate the factored shear force, that is in this case WL by 2. That will be the reaction that is actually coming at this end. Okay, so we have calculated the factored bending moment and factored shear force. Now what we have to do is that, as we were doing in the case of beam, we have just made some assumptions. We have assumed the effective depth to be like this, and now what we will do is that, as we were doing in the case of beam, we will check whether it have been converted to a over reinforced section or not. So for that, what we have to do, we have to use the equation corresponding to balance section, and you have to find out the minimum depth required. Okay, so what we will do, as we were doing it for minimum depth, the limiting neutral axis in this case is observed to be 0.48, and we will use this expression, and from this we will find the value of B by substituting the value of mu as the value which we have obtained here. Mu is 15.97. We will just substitute it here, and we please do note the width is, in this case for the slab, the width is 1000 millimeters. This is the one of the major and repeated mistakes that is seen while we go for valuation. You will be assuming some width like 250 mm. Maybe in the question they might have mentioned that the support is 250 mm wide. So you will be substituting the value of B as 250. That is entirely wrong. In the case of slabs, the B is 1000 millimeters or 1 meter. Okay, so you substitute these values and find the value of D from this relation, and you can see that When you substitute these things, your D will be coming around 76.08 millimeter, which is again less than the value that is provided. Okay, so we have already provided 120 millimeters and the D required is 76.08. So it is safe. It is a under reinforced section. So what we can do? We can proceed with the remaining. So the section is safe. Now what we will do is that we will calculate the steel required. So in this case, how to calculate the value of steel required? So for that we have to use the equation corresponding to under reinforced section, which is mu is equal to 0.87 Fi AST into D into 1 minus Fi AST by this equation, and from this you can calculate the value of area of steel. So once we complete up to this point, I will just tell you how to provide the reinforcement. In the case of slabs, the main difference, let me tell the main difference. In the case of beams, what we were doing is that once you get this value, what you will do is that you will assume some diameter of the bar, you will calculate the area of cross section of this single bar, then you will divide this thing by that, this by area of single bar, and you will provide say 3 number of bars, 4 number of bars, or 5 number of bars, like that. But in the case of slab, we are not actually adopting the same method because the slab will be having a very large dimension, right? So in such a case, what we will do is that we will just make an assumption of the diameter of this bar, say something like 10 millimeter, and we will mention that the center to center distance between the nearby bars. So once we have a slab like this, larger slab like this, what we can do is that we will provide our first reinforcement like this. After that, we will tell we have to provide 10 millimeter 5 bars at say 150 millimeters C by C, center to center. So what we will do is that first of all, we will keep our first bar, then we will take 150 millimeter, we will provide another bar, then again we will take 150 millimeters, we will provide the next bar. Like this, we will continue till the end of our slab. There is no meaning in telling that say you have to provide say 25 number of 10 millimeters bar. No need to tell, we don't tell like that in the case of slabs. We will just mention it like the in terms of diameter of the bar and center to center spacing, and we will see how to find out the center to center spacing so that the AST will be automatically satisfied. So we will see that in the next class. I hope I have mentioned in the last class that in the case of slabs, we will not be giving the number of reinforcement because it is not a good thing, because the slab may be spanning for a larger length and we cannot just give a larger number like that. So it is a normal practice to express. In the case of slabs, we will be providing say once you are going to provide diameter of the bars as 10 millimeters. So what you will mention is that provide 10 millimeter 5 bars be provided, and we have to calculate the spacing between these things. So for that, what we do is that spacing of the bars, and please do remember that we have taken the width as 1000 millimeters. So spacing of the bar will be equal to this 1000 multiplied by area of cross section of one bar divided by the total area which is required. So let's assume that this is 1000 millimeters. Suppose say let me ask you. Suppose the total area that I should provide is say 78 millimeters. That is the area of cross section of a 10 millimeter bar. Say area of cross section of a 10 millimeter bar will be 78.5. And from this equation, what I am getting is here it is obtained as 78.5 centimeter. So how many bars should be provided? Actually, as per our normal calculation for beams, we have to actually provide 1 bar, right? Say if you are getting this as 78.5 and you are assuming 10 millimeter diameter, you know that the area of cross section of a single bar is 78.5. So this is the total required, this divided by 78.5. That will give you 1 bar. So basically you have to provide just 1 bar. So what will be the distance between these things, or what will be the remaining distance in this case? We will be having 1000 millimeter remaining, so that after this 1 meter, what will have? You will be having slab again. So we will be having the slab like this. So in the next stage also you will be providing just 1 bar. After that you will be providing 1000 millimeter again, right? So this is how you will be providing it. So if you see this equation, what they have, yeah. Any doubts? Okay. So let's assume that this is your 1 meter. Okay. And your slab is in total having a length in this direction as 2 meters. The total length, this is your total slab. And please do remember, we are just designing it for 1 meter length. So we are assuming that it is a beam having 1 meter width and thickness. Okay. Right now we obtained AST as, say in this case 78.5. Say arbitrarily I am taking it as 78.5. And I am going to provide 10 millimeter diameter bars. So basically I will be in need of providing one single bar in this 1000 meter. Okay, in this 1000 meter I have to provide one single bar. So basically what will happen is that the confusion uണ്ടെങ്കിൽ ഇതും വേണ്ട. Say first case let's assume like this. I will be just providing a single bar here. Okay. Then from this equation if you see we have the spacing of bar is equal to 1000 into the area of cross section of a single bar divided by the total area. That is what we have done here. Say 1000 divided by the number of bars required. So what I will get is that instead of this I will be having here 78.5 again. So 1000 into 1. So basically the spacing will be again 1000 in this particular case. So after providing this bar, when I consider the total slab, what I will do is that after this reinforcement, what I will do is that I will take a 1000 millimeter length, 1000 millimeter length. Then I will provide the next bar because my slab is actually having a larger dimension. So we have just carried out our design based on 1 meter length, and we obtained a spacing of 1000 millimeters. And in general, what we will do is that when you provide reinforcement in this slab having this 2 meter, you just provide 10 millimeter diameter bars at 1000 millimeter center to center spacing. 10 millimeter pipe at 1000 millimeter C by C. So you will be getting this configuration. Okay. So this is how you will calculate the spacing. Let's check for another case. Say to make things more clear, let's assume again this is 1 meter, say 1000 millimeters. Okay, and again we have some slabs running in this direction, so we please keep that in mind. Okay, so in this case, in the second case, what I am doing is that I am not getting it as 78. Instead I am getting double that of 78.5 into 2. This is the total area I am getting. So again I am going to use 10 millimeter bars. So here I will be having 78.5. Now when I substitute it here, what will happen is that in the denominator you will have the total area, that is 78.5 into 2, and on the numerator we will be having the area of cross section of a single bar. So what I will get here is that 1000 into 1 by 2. So from this you know that this is 2. So actually we are taking the reverse thing here. Okay, 1000 divided by this. So basically you will be getting it as say 1000 into 1 by 2, which is equal to 500 millimeters. Okay, so this is the spacing that you are obtaining from this equation. Say I am trying to provide the spacing like this. So what I will do is that, say if you are starting from this side, say first of all I will be providing a reinforcement here. Then I will take another 500 millimeters. Then I will provide another reinforcement. Then I will take another 500 millimeters so that I will reach this point. So basically, in this 1 meter segment, I will be having how many number of bars? I will be having just 2 number of bars. So the next thing will start in the next part of the slab. So once you have 500 millimeter here, again 500 millimeter. After that, you will be having your next bar in the next segment. It is not in the 1000 millimeter span or the width. Okay, so here similar to this one, you will be having another bar, then you will have another 500 millimeters, then you will have one more bar. Then if further length is there, in the next segment you will be having the next bar. It will be going like this, look like that. So in case if instead of this 2 you are having 3 times, you will be ending up with 3. So the center to center distance will be again reduced to 333.33. So again you will be providing, taking first distance as 333, you will provide your first bar. Then you will take again another 333, you will provide another bar. So one more 333 will reach, make you reach 1000 millimeters. So the next segment will start. So basically, this is how you will calculate. So I just demonstrated how this, whether this equation is correct or not. That's all. So in order to calculate the spacing, what you have to do is that you just multiply 1000 into the area of cross section of one of the bars. So here, since I have taken it as 10 mm diameter, my area will be 78.5. If I have taken it as 12 mm diameter, my area will be different. You have to substitute the corresponding area here, area of single cross section divided by the entire thing divided by the total area required as you obtained here. So in this particular case, it will be 395.67 will be your total area, and area of cross section of single bar will be 78.5. Therefore, I have substituted as 1000 into 78.5 divided by 395.67, which will give me 198.40 as my center to center spacing. Therefore, I am just rounding it down to 190, and I am just mentioning that provide 10 millimeter diameter bars at 190 millimeter center to center. Is it clear up to this point? Any doubts here for anyone? It's clear. Okay, I am assuming that there is no clarifications further required here. So I have just mentioned that refer clause number 26.3.3. Can anyone tell me what will be there in this clause? It is regarding the spacing of bars in the case of slabs. So let's fastly look into the code. So it is basically regarding the maximum distance between bars in tension. Okay, maximum distance, that is a regulation from IS code regarding the maximum distance between bars in tension. So let's see what is the value corresponding to that. In the case of beams also some clauses are given, and in the case of slabs. So right now we are dealing with slabs, so let's look into that. The horizontal distance between parallel main reinforcement shall not be more than 3 times the effective depth of solid slabs, or 300 millimeter, whichever is smaller. So what you have to do is that as a check, after finalizing the spacing, what you have to do is that you just calculate 3 times your effective depth, 3 times your small d. Okay, in this case our small d is 120 millimeters. So 3 times 120 millimeters, which is 360 millimeter. Then we have one more condition, that is 300 millimeter, and the smaller one in this is when compared to 360, 300 will be smaller. So your spacing, the maximum limit of the spacing is, as suggested by the code, is 300 millimeters, but we have provided only 190 millimeters, so it is safe. Okay, this is how you have to perform the check. I am repeating. First thing is that you have to calculate 3 times effective depth. In our case, effective depth is 120 millimeter. So 3 times 120, which will come around 360 millimeters, or 300 millimeter, whichever is smaller. Therefore, 300 millimeter is smaller. So the maximum permitted spacing is 300 millimeter. But as per our requirement, we have provided only 120 millimeter, so it is safe. Now, what is the second condition? The horizontal distance between parallel reinforcement bars provided against shrinkage and temperature shall not be more than 5 times the effective depth of a solid slab, or 450 millimeter, whichever is less. So for the time being, you just understand, we will be, in addition to this main reinforcement which we have designed now, we will be having another set of reinforcement running in perpendicular direction to this. So we have provided this reinforcement in one direction, and again we will be having a similar type of reinforcements provided in the perpendicular direction to this. That is actually provided to take up shrinkage and temperature, and they are actually called as secondary reinforcement. The reinforcement which we have provided right now is termed as primary reinforcement, that is the main reinforcement. Then we will be providing some secondary reinforcement in the perpendicular direction also, and that is the main intention of that is to take care of the shrinkage and temperature. The effect of shrink, as we may expect some shrinkage in the concrete, and as well as the temperature will also influence this. So there is a chance for contraction and expansion for the slab. So in order to take care of that, we need some reinforcement in the perpendicular direction also, and that is the main reason why we are providing secondary reinforcement. Okay, so these are the things regarding this clause. Now we will come back to our PPT. I hope the clauses were clear to you. So once this is done, so we will finalize and find out what is the total percentage of reinforcement that we have provided right now, because we have just rounded this down and we have increased the amount of reinforcement. So let's see what is the total amount of steel we have provided. So therefore the provided steel area is equal to 1000 into area of reinforcement. So from the very basic equation, this thing we are recalculating the total area that is provided. So what we will do is that this is the total area that we will take to our RSS, and the spacing will be brought to the denominator. Right now we know the spacing as 190 millimeters. So 1000 into 78.5 divided by 190, that will give the amount of reinforcement corresponding to this. That is, if you are providing 10 millimeter diameter bars at 190 mm center to center, you will be getting 413.16 millimeter square area of reinforcement at every 1 meter length. Okay. So this is the actual amount of reinforcement that we have provided. Now what we are doing is we are going to calculate the percentage of steel reinforcement. What do you mean by percentage? It is the area of steel divided by the total cross-sectional area. Therefore, area of steel divided by our width is 1000 and our thickness or the depth is 120. So corresponding to this, you will be getting it as 0.344%. So let's see why we are calculating these things, percentage area and other things. So provided steel is this and percentage of steel is this one. Now what we have to do is that we have to come to your code IS4 physics. Let me check which was the page corresponding to that. Say I hope it was 36 or something. This was 39. Yes, here we have something. Depending on the area compression rate, not this one. Yes, this one. So please say again, we have come back to control of deflection, and in the initial stage, if you remember, we have obtained based on control of deflection this span to depth ratio of 20. We were in need of 20 centimeter depth, but I have just merely made an assumption of depth. Let the depth equal to 120 millimeters, that is 12 centimeter, which is very less in compared to the actual requirement. And there I have mentioned that in a later stage we will prove that this is sufficient for the control of deflection. So let's see how to do that. So again we are back at the same thing, control of deflection. So here if you remember, there are some additional conditions mentioned below this span to effective depth ratio. So from this only we have taken the span to depth ratio. So if you see clause number C, let's see what is mentioned there. Depending on the area and the stress of steel for tension reinforcement, the values in A, that is this span to depth ratio, values in A or B, or this one, for in the case of beams having length larger than 10 meter, values in A or B shall be modified by multiplying with the modification factor obtained as per figure 4. So basically what they mention is that if you are providing more area than the required. So in this case, we have seen that we were in need of a spacing of some 198 millimeters center to center, but we have provided a smaller spacing so that the amount of steel will be increased. A much more amount of steel will be actually provided. So that is the condition. Depending on the area and the stress of steel for tension reinforcement, the value in A or B shall be modified by multiplying with a modification factor as obtained from figure 4. So let's see. So basically what they mention is that based on the area and the stress that is coming in our steel, we can modify this effective span to depth ratio. This 20 can be modified by using a modification factor. And let's see how to modify that and how to obtain this modification factor. And they have mentioned that to refer figure 4 for obtaining the modification factor. Let's move on to figure 4. So this is your figure 4. Modification factor for tension reinforcement. You have some curves like this, and on the x-axis you have percentage tension reinforcement, and on the y-axis you have modification factor. And if you see, you have different curves for different stresses coming in your steels. That is Fs value. So Fs is equal to 290, Fs is equal to 240, Fs is equal to 190, 145 to 120, and like that. Likewise, you have different curves, and you are provided with an equation. Fs is equal to 0.58 Fy into area of cross section of steel required divided by area of cross section of steel provided. So here area of cross section of steel required was at a spacing of 198 point something, 198 center to center distance, but we have provided it as 190 center to center distance, and Fy was 415. Then we have 0.58. So let's firstly go back to our slide. So we are just calculating the value of Fs. Fs is equal to 0.58 into Fy into area of cross section of steel required by area of cross section of steel provided. So this is the amount of steel that we have provided. So based on the previous value, this thing, your area of cross section will be AST. This AST divided by B into D, that is 1000 into 120. So that will give the actual required area, and this will give, that is this revised area divided by 1000 into 120, that is 0.344, will give you the area actually provided, area of cross section actually provided. So you know both these values. This is 395 and this is 413. So you just substitute that. Area of cross section of steel required is 395.67. Area of cross section of steel provided is 413.16. You just substitute these values. Then instead of Fy, you have to substitute 415 and 0.58. That will give you around 230.51 MPa. Okay, this is the value for Fs. Now we will come back to our code. So our Fs was 230.51. So basically the value of Fs was 230.51. So if you look into that, that will be a curve in between these second and third curve. So here we have Fs is equal to 240 and here we have Fs is equal to 190, and the required value is 230. So it will be in between this. Okay, and again the percentage of tension reinforcement that we have provided is 0.344 percentage. It is 0.344 percentage. So that will be something around in between these two lines, because this is 0.4. So this will be 0.2. Okay, this is actually equal. Grid is actually equal dividing. So this will be 0.2, and the value required is 0.344. So it will be somewhere after the midpoint of this second grid. Okay, it will be somewhere here, 0.344, and we can go in the upward direction, and we can reach something like this. So as I have mentioned, we will be having a curve in between these two, and if you are coming from the bottom corresponding to 0.37344, it will be reaching somewhere here, and from this point you have to go in the left direction and you will reach somewhere here. Let's assume that this value is something around, say this is 1.6, this is 2. So it may be, this may be 1.8. So this center value may be 1.7. Let's take it as 1.7 or something. Okay. So once you get that modification factor as per this code, what do you have to do? You have to modify this value using this by multiplying this modification factor with respect to this value. So basically our span to depth ratio can be modified as 20 into modification factor. Here I have obtained the modification factor as 1.7. So what I will do is that I will just go back here, and from this curve I have obtained a modification factor of 1.7. So based on the control of deflection L by D, again I am recalculating the L by D ratio as 1.7 into the 20, the first value that's suggested by part A. 20, that will come around 34. Now from this, based on this modified L by D ratio, I will be again calculating the effective depth. So effective depth is equal to span by this thing. Okay, so 34, which will give me 117.65. So this is the required depth, but we have already provided it as 120 millimeters. So basically we are safe. So this is how you prove that even though I have taken a smaller value, even though I was getting a span to depth ratio of around 20, my assumption was safe. Okay, so if you see here, I have assumed it as 120, and I am just now the revised requirement is only 117.65 millimeters. So it is less than assumed value, so it is basically safe. So this is how you should perform the limit state of flexure design in the case of slab. Okay. Now, in the case of slab, moving on to the design for shear, normally we will not be in need of providing any sort of shear reinforcement in the case of slab. But anyway, let's try to see whether we require anything. So before that, one more thing is there. So I'm sorry. So before that, what you have to do is that. So this completes the design of our main reinforcement. So if you are taking the plan view, that is view from top. So let's take this to be the thing, and this was our cross section. So basically, for this span, we have now provided some reinforcements like this 10 mm by diameter bars at a center to center spacing of 190 millimeters. So if you represent this in your plan, you will be getting some reinforcement like this. I hope you are following. So this thing we have already completed now. So and as I told, we will be in need of providing a secondary reinforcement here in the perpendicular direction. So in this direction, if you take a cross section from this side like this, you will be in need of providing some reinforcement like this. This is mainly for preventing the shrinkage effect of shrinkage and temperature. Okay, now we are just going to design this, and there is no much elaborated procedure for this. You just provide 0.12% of your cross section as the AST for corresponding to your secondary reinforcement. Again, this is as per your code. I am not remembering the respective clause. Anyway, there is in somewhere in your code they have mentioned that AST for secondary reinforcement is 0.12%. So just directly calculate that 0.12% of the cross section, that is B into. Please note this is overall depth, B into D divided by 100. So that will come around 168 millimeters. Now, as the secondary reinforcement, we are assuming a diameter of bar as 8 millimeters. So spacing required is 1000 into area of cross section of a single bar divided by the total requirement, and that will come around 299.05. So referring to this clause, since this is very near to 300, very slight 1 millimeter difference. So let's take it as 300 millimeters. That is the only reason why I have rounded it up. And please do remember, we cannot round it up if there is much more difference. Here, it was only 0.95 millimeter difference, 0.95 millimeter. So please visualize the difference I am considering, 0.95 millimeter difference. So that is the reason why I have taken provide 8 mm diameter bars at 300 millimeters center to center. Again, you have to check with the condition of the code, which mentions that it was something like, in the case of main thing, it was 3 times your depth and 300 millimeter, whichever is smaller. But in the case of secondary reinforcement, it is like, I hope it is like 4 times your depth and 450 millimeters. Please cross 4 or 5 times. You just cross check that what is the correct value in the code, in the respective code, respective clause. And we are just providing 8 millimeter diameter bars at 300 millimeter center to center distance. So yeah, now moving on to the case for shear. Now we have designed our main reinforcement, that is primary reinforcement as well as secondary reinforcement, and secondary reinforcement corresponds to 0.12% that we have seen. And regarding the maximum spacing also there is slight difference, so please do note that. Now moving on to the design for shear. So we know that the first step is to calculate the value of tau v, and we have already calculated the factory shear force in the initial step. So substitute the value divided by 1000 into 140, and I think there is slight mistake here. When we calculate tau v, we cannot take it as 140, it was 120. There is slight mistake here. Anyway, so you please calculate the respective value for tau v. So here they have it mentioned it as 0.1261, and the percentage of tension steel provided was 0.345. In the previous case, we have seen that the percentage of steel was 0.345, and as per table 19, we can get the strength of shear strength of steel from table 19 based on 100 AST by BD, that is this value, and your grade of concrete. So it is obtained as 0.23. Now the thing is, there is slight change in the case of slab. So let's go to clause number 40.2.1.1. Clause number 40.2.1.1, that is design shear strength of concrete. Okay, so 40.2 is that, and the design shear strength of concrete in beams without shear. Okay, anyway, that is regarding the beam. Anyway, this is applicable in the case of slab also. So based on table 19, we have calculated the value of tau c. Now it is mentioned in 40.2.1.1 that for solid slabs, the design shear strength, that is tau c, design shear strength for concrete shall be tau c times k, a factor multiplied by tau c, where k has the value given below. So based on the depth of the slab, they have provided different value for k. In our case, our total depth is 150. It is overall depth. Please note again, it is not effective depth, it is overall depth. And in our case, we have provided overall depth as 140 millimeters. So if you see here, we have the last condition as 150 or less. So for all the other cases, we have to take a factor, k factor as 1.3. Now the strength of the shear strength of the slab will be tau c times this 1.3. Okay, so now we will come back to our slide. So tau c is equal to 0.23, that is tau c times 1.3, which is a factor right now we have calculated. So it is coming around 0.30. Now, if you remember, in clause number 26.5.1.6, we will take that 26.5.1.6, 26.5.1.6. So 26.5.1.6 is minimum shear reinforcement. That was we used to calculate that based on an equation, and below that, less than half. Okay, where the maximum? There was a condition mentioned in your code that where the maximum shear stress calculated, that is maximum shear stress means tau v is less than half the permissible value. Permissible value means the strength of the concrete, that is our tau c. So when the tau v value is less than half the permissible value, that is tau c, and in member of minor structural importance such as lintels, this provision must not be complied with. That is, we need not provide any minimum reinforcement. So that is what we are utilizing here. If you see here, the tau v value is 0.1261 and the tau c value is, the modified tau c value is coming around 0.3. If you compare these two values, tau v is actually less than half of this. Half of this is only 0.15, but our tau v value is 0.12. Okay, so in this case, we need not provide any shear reinforcement. So even minimum shear reinforcement need not be provided in the case of slab. So from these things, you can understand that we need not provide the minimum shear reinforcement also. Therefore, we need not provide shear reinforcement in the case of slabs. We have to provide only the main reinforcement and the secondary reinforcement. So once you reach up to this point, what you have to do is that you have to just provide the detailing drawing showing the reinforcements provided in this. So that will have a plan like this. Then you will have a cross section like this here, and here also you will have a cross section to show the secondary reinforcement. So here you will be having some reinforcements like this. Here also you will be having some reinforcements like this, and here again you will be able to see this main reinforcement. If you remember, say corresponding to these values, we will be having some reinforcement like this. When you see it from this side, it will be a line. Okay, on top of this, we will be providing our secondary reinforcement like this. So that is what is shown here. Now what you have to do is that you have to just show it like this. Say 10 millimeter phi at 190 millimeter C by C, and here also. This is say 8 millimeter phi at 300 millimeter C by C. Then you have to show these dimensions. Okay, this one, that value. Here also you have to show the dimensions. This value. Then here you have to also show the main reinforcement. So this is again 10 millimeter phi at 190 millimeter C by C, and here. So basically, this is how you have to provide the detailing. Okay, you have to show all the reinforcement details here, and here you have to also show the thickness. Here also you have to show the thickness. So like this, you have to show all the things here. And to get a better picture of how to show the detailing, you can refer your SP34, which you have already bought during the initial phase of this semester. Okay, so there they have clearly mentioned how to detail one-way slab, how to detail the two-way slab, and other things. Okay, is there any doubts? So that completes our design. So in the next class, we will be actually designing a cantilever slab.